Okay, so this is my presentation of my master thesis project regarding a universal diagram editor where its graphical notations can be created and customized without programming. In software engineering, graphical modeling languages are used to design and document system, for example. However, in current tools, there are some challenges. First of all, we are dependent on software developers to implement these notations, and this is inefficient when the graphical notation developer communicates the requirements. Then the software developer might not interpret the requirements correctly, and they implement the notations wrongfully, and this would lead to later reiterations on the implementation to fix it. And graphical notation developer cannot realize graphical notation themselves because existing tools are difficult to use because they require, for example, Eclipse require programming knowledge to have its graphical notation defined, as does Metated Plus as well. Also Metated Plus, its meta model is difficult to define because it has more layers to it. And this all leads to slow implementations of notations, and it is costly. To which users does this project matter to? It matters to graphical notation developers who can then use our tool developed in this project to define a graphical notation themselves. And it also matters to software developers who can focus on other programming tasks which are more important than to configure these editors. And it also matters to diagram creators who can use up-to-date graphical notations to create their diagrams. The agenda for today, we will go through the objectives of the project and the features of the software build, and then a live demo of the software, and then how the software was designed, and then a conclusion and future work on the project. So the primary goal of the project was to develop a universal diagram editor, and by universal diagram editor we mean an editor configurable by anyone who already knows how to use these meta models and design them. And the configuration should be done in a low-code form, while still maintaining high flexibility and making it possible to define edge cases in graphical representation of the concepts. And all in all, we go from these slow and hard to use tools to a more easy to use and no code generation required, so it is faster to define these meta models notations. And this also makes it possible for graphical notation developers to define notations independently. The features of the software. So currently the software can define graphical notations through a meta model configuration panel, which you can see on the left. And it also has a graphical representation panel to define the representation of the concept. And then the tool mostly maps these representation to meta model concept automatically, but some mappings has to be defined explicitly by the developer. It also contains a diagram editor where these graphical notations can be used directly when they are modified. And it also has a diagram validator, a lightweight diagram validator, which uses a custom constraint language. And currently it only supports live constraints, which are these hard rules where the user is not allowed to perform a task if it violates a drawing, if it violates a constraint. There are also offline constraints which do allow the users to perform a draw action, even if it violates a constraint, but then it will flag that action as wrong when validating the diagram, but offline constraints we don't have. And we have this validation mechanism that uses the constraint language to, for example, to perform these validations. And this is the message that we show the user when they violate a constraint. Now I want to show you a demo of the tool. So this is the editor tool, and we can start off by selecting a language to use, a graphical modeling language. So for example, PitchNet currently contains a place, which is represented by a circle, and an arc, which is represented by an arrow. But we are missing the transition concept. So let's go ahead and define that. So first we go to the configure panel. Then we select our language, and then we select the elements that our language consists of. And this basically represents this meta model of PitchNets, and we are missing this transition. First of all, I just want to show you how arcs or edges are represented or defined. So in edge, we can see its preview on the right side, and then what we can configure in edge. We can make it a double line, and we can define the color of the line as well. And we can see that in the preview. And then we can define the width of the line and other style properties, such as making it dotted, this pattern. And then we have these source markers, and the source marker we can define to be open, closed, or none. And we can do the same for the target marker. So now to define the transition concept, we can write the name of the element, and a transition is a node. And we can see here that a transition refers to the node concept through a supertype association. So let's add that so we can see a supertype, and we add it to the node, and then we add it, and we save the transition concept. But we can see here the transition does not have a graphical representation in our modeling language yet, so let's define that. We go to the draw panel, and we simply just draw our transition, and we add the connection points which Reactflow needs to connect edges to nodes. In Reactflow, we also need to define on which position these connection points are placed. Yes. So now we have defined that. We can also choose to add specific style properties to the square, background color and border, but we won't do that for this one. So now we can go back, and now the transition concept should be available in our language directly without generating the diagram editor code, and we can see that here. So now let's try to instantiate a diagram. First I want to show you the instance model, that it doesn't have anything in it right now. But let's try to drag a transition onto the canvas. And we can see here that the instance model now contains a transition. And we can also see the layer, the graphical features that it has, the layers of features. So it has 4 connectors and a square. And yes, we can try to draw a more complete diagram. And then we can draw edges from connection point to connection point. The edges that we select from the language are the first one, but currently we only have arcs in this language, so we will always draw an arc. And then there can be specific attributes on the edge that we can define by double-clicking if it should look differently or such. And now I want to show you the custom constraint language in use. So if we try to add an edge between a transition to a transition, this is invalid. So When I do that, we will get invalid connection based on the constraint that we have added to the meta model. And yes, okay, so now I just want to show you how compartments work. And for this, I will select the UML class diagram language to show it with attributes. First, I will show you in the representation editor how compartments are added. So in the class, so first of all, we have a label on top, which refer to a local attribute of the class in the meta model. So this should be the name. So we will show the name of the class here. And then we have a compartment, which refer to a reference of the class. And here we have selected attributes with a vertical layout, so the attributes extend downwards. And yes, now let's see that in action. We can try to draw a class, and we will name it dog, for example. And we can see it is reflected. And then if we add attribute, let's say the name of the dog and then a string type, then we can see that here. And let's now add another attribute, for example, age of the dog, which should be an integer. And now these are defined, and we can see that they extend downwards. And lastly, we can try to export the created diagram, and we can view it in a picture format. And this is the one. Okay, and now I will go back to the presentation. So the way that our tool is designed is, first of all, we have a core model which is used to instantiate these meta models of modeling languages. This is done by the graphical notation developer who uses the notation editor to define these meta models within the structure of the core model. They also define the additional constraints for the meta model and the graphical representation of the concepts of the meta model. The system has a mapping mechanism between these two models, and all these three models, they make up for a graphical notation. This graphical notation can be used by the diagram creator in the diagram editor to create instance models. And these instance models always keep track of which type they refer to in the meta model. So for example, if you instantiate a class, it will refer to the class concept in the meta model. The purpose of our core model is to define these meta models of modeling languages, and we use a simplified e-core model. So now I want to explain the features that our core model supports. So consider this diagram down here, which is an instance of the core model. And it is an instance because, so for example, this thing here, package, this is the graphical representation of this thing here. So a package concept. This package concept contains multiple classifiers, and classes are classifiers. So this is valid here. We can see it here, that the package contains multiple classes. These classes can have multiple attributes, which you see in this reference. And an attribute itself can refer to a data type, for example, string, and that we can see here. And a class can also have multiple references. And a reference points to another classifier, which a class also is. So we can see that the owner reference points to the person, and oppositely the person points to the car through the car reference. And this meta model is flexible because it's a meta model for class diagrams, and class diagrams can be used to model modeling languages. This form of representation is called concrete syntax, where we can see it graphically, but the underlying structure of this diagram is seen in the abstract syntax. It contains of the same element that I just explained, where a package points to classes, and classes have their attributes, and attributes have their data type. And references, they have this opposite reference, which means to each other, which means that the two references can be merged into one graphically. So between these two models, there are mappings going on. So we say that this concept here, package, looks like this, and this class here is represented like this, and this reference is represented like this. So we need to have some mappings between them, and we do that by a mapping model. The purpose of this is to map these graphical representation to metamodel concept. And one graphical representation can have multiple graphical features. These features can, for example, be static or advanced. Static features are those that can be directly linked to metamodel concepts, which are, for example, shapes. So, for example, in classes, a class can be directly linked to a shape. However, advanced features are those that are dynamic in their appearance. So, for example, attributes in a class can extend or shrink the rectangular shape. Yes, and our mapper model is part of the graphical representation model. Now I want to show you an example of a mapping on a class concept. So first of all, we have the overall representation being a node, because a class is a node. And this representation consists of multiple graphical features, which we also call shapes. First of all, we can see a rectangle shapes, which is this thing. And then we can see a label, which is this label, representation item. And labels consist of a format string, which points to the metamodel concept and attribute of the metamodel concept. So this is, for example, the name of the class concept. Then we have a compartment for the attributes. The compartments always points to a reference because it has some multiple behavior. And here we can see it points to the attributes reference. The content of a compartment is defined by pointing to another representation item, which should tell the format of the content. So here we can see it points to a label, and this label's format are references to the field name, which is the attribute name, and the type is the type of that attribute, is the data type of that attribute. Yes. Similarly, it's done with edges, but they just have some different shapes. An edge always have a line shape and two head markers. And the two head markers points to the source and target reference of that edge in the meta model. So yes. We use React Flow as the framework to implement the diagram editor. React Flow contains nodes, edges, and handles. And we have implemented a layered way of rendering shapes. So all these shapes that you can see here on the left in our representation model, we render them like this in the code. So for example, for a node, we render each shape differently. And yes, we also have constraints and validation. And here we have implemented a custom constraint language, which is inspired by OCL. So first of all, we can define the constraint like this in our tool. So it contains a condition string, which is this, and a type being live or offline. And the next step is to pass this condition string into an abstract syntax tree, which we can then traverse with logic to evaluate. And for example, when we see a call expression, we go into the call case, and then we check if we have this method kind of, which we do have in the code, which can perform this type check. So we would check in the meta model of that source object, for example, and check if the type that it's referring to in the meta model is indeed a place. And then we would do the same for the rest of the calls. We also evaluated the tool, and we found some strengths and challenges. So it was possible to customize these graphical notation without programming. However, currently we only cover Petrinets and UML class diagrams. Petrinet, we don't have tokens and bar-shaped transitions. And for UML class diagram, we don't have operation and some other association types. We do the customization with low code and focusing on drag and drop features. And also we do not require any code generation after every customization. Challenges that we found when using the tool was that defining these meta models is complex and required guidance. And we had limited graphical features, so only these rectangles and circles and compartments. Also, our performance decreased when created larger diagrams over 70 elements on the canvas. And when we exported diagrams that were over 70 elements, we were excluding some elements. And future work could be to improve the meta model configuration panel, which you see here. And this can be done by instead doing it more graphically. So using our diagram editor, where we can provide the UML class diagram language that the user can use to draw the meta model instead of defining it textually. And that can also be to optimize performance for larger diagrams when having many elements on the canvas. And it could also be to support for additional graphical features. For example, in sequence diagrams, they have node-to-node relations, so nodes containing other nodes. Currently, our tool supports only node-to-reference and reference-to-node. Node-to-node is, for example, used in lifelines in sequence diagrams. When they have this messaging box on the lifeline itself, that is a node-to-node relation. Support for that. And then it could also support advanced constraint validation for these offline constraints, where we show a list of violated constraints in a created diagram. And it could also be to improve the saving. So that could be made done file-based, where you would export this instance model, and then you can load it at a later point. Because currently you can only work on one diagram at a time because it's stored in local storage of the user. And exporting can be done to include all elements in the canvas because it currently excludes some. There can also be higher customization flexibility in the drawing. For example, with arrowheads, currently you select what type of arrowhead it should be, open or closed or none. But that these arrowheads could be made drawable. So for example, in SVGs, you can draw these arrowheads instead. So we just more have flexibility when defining them. The conclusion of the project. So the contribution made was we showed that diagram editors could be improved in their system design, and we did that in demonstrating a universal diagram editor where its graphical notations can be customized without programming and without requiring code generation. And the key challenges in the project was to design the core meta model from the e-core to fit our needs, and also defining these layout mapping mechanisms, and always ensuring high usability for the user. Yeah, that is it.